Thank you for this invitation. And I'm sorry I can't be here, but as introduced, this is a talk about neutron scattering. Let me find my pointer. Here we go. Yes. Right, so here's the summary. Yes, I shall briefly introduce conventional magnets because neutron scattering is a technique that can be used to investigate magnetism. So briefly, conventional magnets, then I'll talk about neutron scattering concepts, and then techniques like neutron diffraction and inelastic neutron scattering. So diffraction looks at magnetic structures and inelastic neutron scattering looks at magnetic excitations. And then spin waves, which are the type of magnetic excitation, a very common one, the calculations and examples of measurements. And then if there's time, I will go on to quantum magnets and how, with an example of measurements with neutron scattering and frustrated magnets. So conventional magnets, just a brief refresh of your memory, of course. So what we expect for a magnet, we have a material, it has magnetic ions on its lattice. These magnetic ions interact with each other. And then we expect, but because of the interactions, that the system would be able to develop some type of long-range magnetic order as you cool down. So here we have high temperatures. At high temperatures, the spins are fluctuating because of the temperature, but as you cool down, then the spins start to see each other, the magnetic moments on the ions start to see each other, and then they lock into a particular type of order where they remain in a fixed position relative to each other for a long time. So that would then be the ground state, which has magnetic order. And you would expect, so you would expect that magnetic order that would appear as in a neutron experiment as new Bragg peaks, magnetic Bragg peaks. So we would expect, a lattice would have structural Bragg peaks. So this is a reciprocal lattice that would be measured, could be measured by neutrons. These are two reciprocal lattice directions. You would expect that, of course, you have a lattice and you have a nuclear structure. The crystal structure would give rise to structural Bragg peaks or nuclear Bragg peaks. But when you cool down, the magnetic order also gives rise to Bragg peaks, and these are called magnetic Bragg peaks, and this occurs below the transition temperature. Now, when you're at this cold temperature where you've got this long-range magnetic order and you've got these Bragg peaks, you would expect some excitations, and the typical excitations are spin waves. These are the fluctuations of the spins about their ordering directions. So they're a collective motion of the spins about the ordered ground state. Here they are depicted as a small deviation from antiferromagnetic order. And this, of course, is a time-dependent deviation. And of course, as you see, a spatial-dependent deviation. So this is a real space picture. And then what we would expect in reciprocal space, which is what neutrons measure, we would expect to see these spin wave excitations as a sinusoidal type dispersion as a function of energy and wave vector. For example, these are the spin waves of a ferromagnet, and these are the spin waves of an antiferromagnet. So these are the things you can measure with neutrons. So now I shall start with basic concepts of neutron scattering. Okay, so neutron scattering is an experimental technique used to study magnetic properties of materials, but also structural properties of materials. So what is the neutron? Well, as you know, it's a nuclear particle. It has a mass similar to the proton found in the nucleus alongside the proton. It has no electric charge and it has a spin. It's a spin half quantum number. Now, because of its spin, its spin angular momentum, it has a magnetic moment, which is given here with the nuclear magnetron. So this is the moment. And interestingly, it also has a finite lifetime, at least when free, not obviously inside a nucleus. So it can last for 15 minutes. That's its lifetime. Now, it's a quantum mechanical particle, obviously. And so when you're thinking about neutron scattering, you think alternatively in a wave picture or in a particle picture, and then these pictures alternate. So, so you think about creation of neutrons, then you think about a number of neutrons, and you're thinking about particles in a particle picture. And then you scatter neutrons. So you fire them at your sample and your sample scatters them. And at this point, you think about them as waves. You're doing diffraction or interference. And then when you detect the neutrons, the scattered neutrons, you detect the number of neutrons. And so you think again about particles. And so you alternate between these pictures. Now, the neutron has a momentum, which is its mass times velocity, of course. But because it's a quantum mechanical particle, its momentum is also Planck's constant times the wave vector, k. So momentum, mass times velocity equals h cross k. So immediately you can put these together and write the velocity of the neutron in terms of its wave vector, or its wave vector in terms of its velocity. Now, being a particle, of course, it has a wavelength. The wavelength is related simply to its wave vector. The wavelength is 2 pi divided by the wave vector. So now we can rearrange this and write the wavelength in terms of the wave vector, or the wavelength in terms of the velocity. Now it has a mass, so it has a kinetic energy. And if it's moving, yeah, its kinetic energy is given by its mass times its velocity squared. But we know its velocity, that's related to its wave vector. So we can write the energy in terms of the wave vector squared. The point I'm making here, basically, is that we have properties of the neutron like velocity, energy, wavelength, and wave vector. And if you know one of these, you know them all. So they're not independent properties. Okay, so now question is, to be useful for us, the neutron has to interact with matter. So we can't do scattering if there's no interaction. So the neutron interacts with matter in 2 ways, via the strong nuclear force, which is very short range. So it sees nuclei within the material that you're studying. So it can be scattered by them. Now the neutron also, so I mentioned it has a magnetic moment. And so that makes it able to see magnetic moments inside the sample. So basically it can see small magnetic fields inside materials. And it's scattered by them via its magnetic moment. So if there are unpaired electrons inside a material and they're going around their orbits, or obviously they have a spin, they are creating small magnetic fields within a material, and then the neutron is scattered by that because of its magnetic moment. So here in this picture, the neutron is the red one. The neutron, so this is, here we have a material. We have the nuclei, that's the dot in the middle, and then we've got one unpaired electron going around the nucleus. And then we've got a lattice of these ions. And now we fire our neutrons into this material, and the neutron can see the nuclei and is scattered by it. The neutron can also see these unpaired electrons and is also scattered by it. So where do neutrons come from? So there are two sources of neutrons that are used for experiments. So the first one is the fission process. So the fission process is when the atom is split, and sometimes a byproduct of that is not just that the atom is split, but that there are also neutrons produced. And of course, the example of this is uranium. So if we have a uranium nucleus, so actually it has to be the special isotope 235 of uranium. This is uranium, symbol for it. And then a neutron comes along and it's captured by this uranium nucleus. So the neutron comes along, it's absorbed, the uranium becomes 236. It gained a nucleon, but this is an unstable state. So soon after this, it splits, for example, into barium and krypton. And in the process produces also 3 neutrons and a lot of energy. Right, and of course, these neutrons, these can be used for neutron scattering, and the energy is interesting because it's the source of nuclear power. Now, we've got 3 neutrons and they have a lot of energy. And so these neutrons can go on to find new uranium nuclei, get absorbed, cause the uranium to split, producing more neutrons and more energy. And this is known as the chain reaction. So this is what happens inside a nuclear reactor. So in a research reactor, the neutrons can then be used for neutron scattering experiments. And there's a research reactor in India, in Mumbai. Now, the second way to produce neutrons is using spallation. So this method, basically, it's a particle accelerator, and the particle that is accelerated are protons. So protons are accelerated to very high speeds, close to the speed of light. And then they are fired into some heavy metal target. And because of their very, very high energy, they send the heavy metal targets. So for example, I'm talking about mercury or tungsten as the metals that might be involved. They send the ions in that target into a highly excited state. So they give them the energy, the ions go into a highly excited state, and then the ions start giving off neutrons and protons. And in this process, you can get very high energy neutrons, maybe 15 to 20 for every proton that arrived at the target. And then these neutrons can be slowed down and used for experiments. Okay, so why doing neutrons, or what is the benefit? So I've pointed out, yes, that neutrons are good for magnetism. They can see magnetic features. Another thing that neutrons are good for is inelastic scattering. So so the neutron is able to give some of its energy to a material and create an excitation. And then we can, by doing this, we can map out excitations in materials, excited states in materials. And so I show here, so what's particularly good about neutron scattering compared to other methods is that if we look at the energy of the neutrons, so I could take some thermal neutrons, for example, here. Thermal neutrons is just a way to categorize their energy. So typically they have energies of the order of milli-electron volts in the range, for example, 5 to 100, but we can get slower neutrons. The good thing about this is that these energy ranges are similar to the phonons or spin waves that you might see in a material. Typical energy scales of condensed matter excitations. And so I told you that when you know the energy, you can immediately calculate the wavelength of the neutron. So neutrons, let's take 20 milli-electron volt neutrons, typical phonon energy. We take 20 milli-electron volt neutrons, and they have a wavelength of 2 angstrom. And 2 angstrom is a typical interatomic distance that you get in materials. So we've got energy that's well matched to the excitations and a wavelength that's well matched to the distances in condensed matter materials. And this nice matching means that it's very easy to follow excitations throughout the whole Brillouin zone to get a complete picture of the excitations and to also be able to achieve this with good resolution. So if you compare, so if we take 2 angstroms, let's say 2 angstrom wavelength, but this time of X-rays, now we're in kilo-electron volt energy range. So this is much higher than condensed matter excitations, and it makes the experiments more difficult, and also the energy resolution is less favorable to measuring the excitations. So now another advantage of doing neutron scattering is that the neutrons are weakly scattered by materials. So actually, when you do a neutron scattering experiment, you fire your neutrons at your sample, and most of the neutrons pass through the sample to the other side and just continue on in their direction. So it weakly scatters. Only a few neutrons are actually scattered by the sample. And why this can be advantageous is that it means that you only get a single scattering event. So the neutron is either scattered or not scattered, but it's rarely going to be scattered twice. And this makes the calculations, so when you want to compare your results to a theory, it makes the calculations much easier, and it makes the comparison between experiment and theory much more quantitative. So here on this graphic, we have different elements. So here we have atomic number, and then we have some calcium, cobalt, iron, etc. And then on this axis, we have what is the penetration depth of the neutron into calcium or iron or cobalt or materials with these atomic numbers. And you see it's of the order of centimeters, so 10 to the minus 2 meters. So this gives the idea of how far the neutron can pass through a sample before being scattered or absorbed. And you can contrast that with X-rays, where the X-rays typically penetrate microns. Okay, so now getting closer to experiments, I want to talk about the fate of the neutron. So we're going to set up an experiment, and we have our neutrons, and they're all moving. We've arranged it so all our neutrons are moving in one direction. We have a beam of neutrons, and then they're going to arrive at our sample. So here we have our sample. There's our sample. And then we have the neutrons. These are represented by these arrows. And they arrive at the sample. And then 3 things can happen. So most of the neutrons actually pass straight through the sample because the sample scatters weakly. So these are known as the transmitted neutrons. Some of the neutrons arrive at the sample and come to a stop. These are the absorbed neutrons. And then the other thing that can happen is that the neutron changes its direction after or during its, when it reaches the sample. And these are known as the scattered neutrons. So they come out at a different direction. So when neutrons are incident on a sample, they can be transmitted, scattered, or absorbed by the sample. And now we can place our detector. So we could put our detector here and we measure the transmitted neutrons. And this is a type of microscopy. So it's not typical neutron scattering that we normally talk about. It's actually a type of imaging where you can image the properties of the sample in terms of its ability to, or in terms of its sort of density. And this is actually used for engineering experiments when you want to look at large components or industrial components. Now, we could also place our detector somewhere out at an angle, so not here, but somewhere out here, so that we capture the scattered neutrons. And then this provides us information about, then we're getting the interference pattern. This provides us information about the positions of the atoms in the sample and also their magnetic moments. Okay, so I'm now going to talk about neutron scattering. So that this is where the detector is placed at an angle, not at the straight through position. So from now on, I'll just talk about neutron scattering. So the basic idea is we have neutrons. They have a known wave vector and energy, and of course, then we also know their velocity and their wavelength. They arrive at the sample, and we're interested in collecting neutrons that are scattered by the sample. So we put our detector at an angle 2 theta to collect the neutrons that arrive at this 2 theta angle. And we're interested in things like their wave vector and energy. So neutrons are scattered by the sample, and the scattering pattern that you get is a specific function of 2 theta. So the scattering pattern as a function of this angle 2 theta is going to be characteristic of this sample. So it's going to tell us things like where are the atoms in the sample, where are the magnetic moments, and where are they pointing. And also what type of excitations do we have. So now during the scattering process, the neutron energy might be unchanged. That's where the incident energy, EI, equals the final energy, EF. So that's called elastic neutron scattering, where the energy of the neutron doesn't change. So now it should be clear to you that if the energy of the neutron doesn't change, then we did not create an excitation in the sample, but we just scattered it. It went off at a different direction. Now, alternatively, the neutron can come along and give some of its energy to the sample and create an excitation, for example, a phonon or a spin wave. And this is known as inelastic neutron scattering. So inelastic neutron scattering is where the final energy of the neutron is different from the initial energy of the neutron. So one way to picture this is to think about scattering triangles. So of course, during the scattering process, there cannot be a change in the total energy. So in fact, if the neutron does lose energy or gain energy, then that energy has to be given to the sample. So that's energy conservation. The change in energy of the neutron, which of course can be written in terms of its velocity or in terms of its wave vector, equals the energy given to the sample, which is donated by H cross omega. Now, of course, we also have conservation of momentum. So the change in wave vector of the neutron, so that would be Ki minus Kf, must equal the momentum given to the sample, or the momentum where we look in the sample. So Q, which we denote as H cross Q, and then Q is called the scattering angle. So Q is the difference between Ki, the initial wave vector, and the final wave vector of the sample. So important point, of course, is we're talking about scattering. We're talking about neutrons changing direction during a scattering process. So these are all vectors. So we're talking about the vector difference of Ki and Kf. Now, for elastic scattering, so we can draw a scattering triangle for the scattering process. So for elastic scattering, H cross omega equals 0, which means that the modulus of the initial wave vector and the modulus of the final wave vector of the neutron must be equal. So that's that statement. So now we're going to draw the scattering triangle, and then we need to represent them by arrows which have the same length. But of course, they don't have to have the same direction. So here we have our sample. And then we have our neutrons that arrive at the sample, and the neutrons are represented by this arrow, which has a length of modulus Ki, wave vector of the initial neutrons. So it represents the wave vector of the initial neutrons, and its length is the modulus of Ki. And then it's scattered. Then the neutrons are scattered at an angle 2 theta. Now I'm talking about an elastic scattering event. Therefore, the length of the final wave vector must equal the length of the initial wave vector. But of course, the direction has changed. Okay, so now we can make a triangle. So the difference between Ki and Kf is the wave vector Q, the wave vector transfer to the sample. Okay, now we can do some maths. So we have this angle 2 theta, so then we can say, oh, well, that angle is theta, this distance is Q over 2. And then we can do some maths. Sine theta equals Q by 2 over K. That's doing trigonometry here. And then we can get Bragg's law. So what does this mean in an experiment? It means that now I've drawn it a different way. We've got our sample, we've got Ki, we've got Kf, and we've got Q, the wave vector transfer given to the sample. So what are we going to see in our detector? Well, if we just put our sample down without thinking about its orientation, probably we won't see anything. But if we put our sample in a chosen orientation such that this wave vector Q lies along a reciprocal lattice vector of the sample. So here, this grid represents the reciprocal lattice of the sample. And this is these are the reciprocal lattice vectors. So if Q lies along a reciprocal lattice vector of the sample, we're going to see signal in our detector. Yeah, Bragg's law. So that was elastic scattering. Now, inelastic scattering is where the neutron gives some of its energy to the sample to create an excitation. So the difference in energy of the neutron before and after scattering, which could be written in terms of its velocity or its wave vector squared, equals the energy given to the sample. Now we can draw some triangles again. So here is a scattering triangle for inelastic neutron scattering. So you can see that we have the initial wave vector of the neutron. We have the final wave vector neutron. The difference is this angle 2 theta. This, yeah, there you are. The difference in direction is the angle 2 theta, and their vector difference is the wave vector q, which is the wave vector of the sample. So what this represents, you notice that ki is larger than kf. So the modulus of kf is smaller than ki. Now, if you think about energy, that means that the final energy of the neutron is smaller. If we look here, the final energy of the neutron is smaller than the initial energy of the neutron. So the neutron lost energy during this scattering process, and therefore it created an excitation at the wave vector q. So this represents the neutron loses energy and an excitation is created at wave vector q in the sample. Here's a different one. Now kf, the final wave vector of neutron, is longer than ki. So the neutron actually gained energy in this scattering process. It absorbed some of the energy of the material. It destroyed an excitation inside the sample. And that excitation which it destroyed or absorbed was at the wave vector q. Now we can go into more maths, but there's not really time for this. I just want to introduce the equation. So if you want to do the calculation properly, you need to calculate what's known as the magnetic cross-section. And here it is. And it contains these wave vectors I talked about, some constants, probabilities of the material being in various states. There's conservation of energy, of course, which is represented by this delta function. But the interesting part here is this matrix element. So this matrix element is the matrix element between the initial state of the neutron and the sample. So it's the wave vector of neutron, the spin of the neutron, and the state of the sample, and the final state of the neutron and the sample. And what appears inside this matrix element is V, and V is the interaction between the neutron and the sample. So this is basically the heart of the neutron scattering cross-section. This is what one needs to calculate. So I told you there were two types of scattering of the neutron. So the neutron can scatter from nuclei within a material, and it can scatter magnetically within the material due to the unpaired electrons. So here, if we're just talking about nuclear scattering, so this is the lower one here, then the V, this interaction, is given by a delta function. And the reason why it's given by a delta function is because it's a very short range interaction. And apart from some constants, the delta function is weighted by this quantity B, where B is a property of the nucleus, and different nuclei have different quantities B, known as scattering length. Now, if we're talking about magnetic scattering, then V is the interaction between the magnetic moment of the neutron and the magnetic field that it encounters inside the sample. Right. And as you can see, this is much more complicated. So why would there be a magnetic field inside the sample? Well, if you have unpaired electrons and they're going around in orbits, they are like current loops and they create a magnetic field. But also just the aspect that an unpaired electron would have a net spin also creates a magnetic field. And so this magnetic field is related to the spin and the orbital angular momentum of the unpaired electrons. So here is what happens after you work through the cross section. So again, I won't go into detail. I just want to point out some features. So there are a lot of constants here, some delta functions that preserve. Well, there's a lot of constants here, but the interesting part is this scattering function S. S is given here. So the main part in this function, so I'm talking about magnetic scattering at this point only, not the nuclear scattering. So inside this function S, which appears inside the cross section, is this part here, where you see the spins, and these are the two spins. It's a two-spin correlation function of spins inside the material. So at the heart of the magnetic cross-section is this two-spin correlation function. And it describes how two spins inside the magnetic material you are studying, which are separated by a distance Ri minus Rj and by time t, how they relate to each other. It's the correlation function. And if you notice, this correlation function, so it's the spatial and time dependent correlation function of spins inside the material. You notice that because of this integration, we actually take the Fourier transform of it in time and also in space. So basically, what magnetic neutron scattering measures is the Fourier transform of the spin-spin correlation function. And another way to say this, if you can calculate the Fourier transform of the spin-spin correlation for a given material, then you can make a comparison, a quite direct comparison between neutron scattering experiments and theory. Right, so now I'm going to talk about some techniques. So that was neutron scattering in general with emphasis on magnetic neutron scattering. So now I'm going to talk a bit more about doing it in practice. So we're going to do neutron diffraction. So neutron diffraction is interested in the static properties of the material. So it's not interested in excitations, it's interested in things like where are the atoms inside a material and where are the magnetic ions pointing inside a material. So in neutron diffraction, well, one method is to use a fixed wavelength. So we use a fixed wavelength of neutrons. So they come along here. Actually, we use a monochromator. So the monochromator chooses a particular wavelength of neutrons. I'll talk more about that later. And then these neutrons go towards a sample. So here we have the sample. The sample you notice is in this cradle. That's because we might want to rotate the sample to reach particular Bragg positions. And then we collect the scattered neutrons scattered by the sample in the detector. So we have Ki, our incident wave vector of neutrons. We have Kf, our scattered neutrons. We've put our detector at the angle 2 theta, so we're measuring in the detector the scattered neutrons at this 2 theta angle. At the moment, I'm interested in elastic scattering, so I've assumed that Ki equals the length of Ki equals the length of Kf. So then we can think about the scattering triangle Q. Q is the difference between Ki and Kf. So here we have it. We can rearrange our arrows to make a scattering triangle. So now you might think, well, maybe you put your sample in, but you weren't sure about its orientation. So the sample went in, you put it on its position, you're looking in your detector, probably you won't see anything. So if you just put your sample down randomly in position and then counted the neutrons in the detector, probably you don't see any neutrons. Because you're only going to see neutrons when a reciprocal lattice vector, so here I've drawn the reciprocal lattice vector of the sample, these are the pale blue dots, when a reciprocal lattice vector of the sample, I have to rotate the sample until a reciprocal lattice vector of the sample points along this wave vector Q. Then I see some neutrons in the detector and I can measure that Bragg peak. Okay, and then I want to measure another Bragg peak. I have to change the orientation of the sample. I also have to match the length of, I have to also match this angle 2 theta for the Bragg scattering law, according to Bragg's law, for that new Bragg peak I want to measure. And I can continue like this and measure lots of Bragg peaks. Now, coming back to the monochromator, so how do you get a single wavelength, or how do you choose your wavelength? So when the neutrons are produced in the reactor or in the spallation source, you actually get a white beam or a large wavelength distribution of neutrons. So you can think about like a distribution. This could be wavelength on the x-axis and number or flux on the y-axis. And then you might have a distribution like this. And but you want to get a single wave vector to do the experiment. So you need to select a single wave vector. And actually this can also be achieved by Bragg scattering. So you have another crystal, but now it's a known crystal, one that's well known and one that scatters neutrons very well. And you put that before the sample. And this crystal has a known d spacing. And you send the white beam of neutrons to it. And you make sure that you've chosen the correct angle 2 theta to get Bragg scattering from your monochromator crystal for the particular wavelength that you want for your experiment. So this also uses Bragg's law. And of course, the remaining neutrons, which don't have that wavelength, are going to pass through the monochromator crystal. So this is a picture of a monochromator. Actually, it consists of 7 crystals in this case. The reason for this is that you can then focus the monochromator to get more flux. Typical monochromator crystals are graphite, copper, germanium. Now, so far I've talked about measuring a single crystal, doing neutron diffraction from a single crystal. And you might notice that you've got to orient your crystal and you've got to know what the Bragg peaks are. Also, you've got to have some knowledge, prior knowledge, because you've got to set your 2 theta angle to known Bragg peak positions in order to see something. So actually, it can be useful to measure a powder sample where if you don't know very much, you can still see your Bragg peaks, even if you don't know where you expect them to be. So a powder consists of many little crystals. That's basically what a powder is. And these little crystals, maybe microns in size, have completely random orientations, and every possible orientation of crystal is present inside the sample, your powder sample. So this means that if you're thinking about Bragg's law, or if you're firing your neutrons at your powder sample, then there's going to be some crystal inside the powder that satisfies the Bragg condition for the wavelength of neutrons that you are using, and also is correctly oriented in order to scatter the neutrons according to, for example, one of the Bragg peaks. And instead of getting Bragg spots, what you get are these rings, because of course they are actually rings of constant 2 theta angle. So instead of a single Bragg spot, which is what you would get for a single crystal, you've got a powder with every possible orientation of the crystals. So you actually get a ring which you can think of as very many little Bragg spots, each satisfying the Bragg condition, and all at a constant 2 theta angle for example, the 220 Bragg reflection. And you get other rings. Now this is other crystallites which have different orientations, for example, and they satisfy the 200 Bragg peak or the 100 Bragg peak. So these are known as Debye-Scherer cones, these rings. And they are cones of constant 2 theta angle, and you get one for each Bragg peak. So now what you can do is you can scan your detector. So we can go from a low 2 theta, we put our detector here, and we can now scan from a low 2 theta to a high 2 theta angle, which can be translated, for example, into Q, wave vector transfer. So we can, and then what you would see in that scan are a series of peaks. And what you're doing is you're scanning through these Debye-Scherer cones. And as you cut through each one, you see another peak. So this tells you what peaks you have and how intense these peaks are. And then you can use this information to work back, where are the positions of the atoms? What type of atoms do I have? So in practice, this is a diagram of the instrument. So we have our neutron source here, and then the neutrons come along, and at this point, there's still a white beam of neutrons. So we've got a range of wavelengths. They go through various slits and collimators until they arrive here at the monochromator. And now we've chosen the monochromator angles to select one wavelength of neutrons. The rest of the neutrons now pass through. So after the monochromator, we have one wavelength of neutrons. So then after some more slits and etc., we come to the powder sample, which is here. And then the powder sample is going to scatter those neutrons according to Bragg's law. And then we're going to measure those scattered neutrons in a bank of detectors placed around the sample. And these detectors cover from low 2 theta angle to high 2 theta angle. And typically what you see in the detector might be, so this may be one of these detectors, is this picture here where you see you see a part of the Debye-Scherer rings. Now in practice, here is a measurement. This is strontium cobalt vanadate. Now strontium cobalt vanadate has a crystal structure, clearly, but it also has a magnetic ion, that's the cobalt. And below a temperature of 5.2 Kelvin, the magnetic ions of the cobalt order. So it has a transition at 5.2 Kelvin. Now, if we're measuring at 8 Kelvin, which is above this nail temperature, this is what we might see. These are the series of Bragg peaks. This is a powder measurement, and we see a series of Bragg peaks. And these Bragg peaks are related to the crystal structure. And if you fit the crystal structure, this is what you get. So here's the unit cell, and then we have the cobalt ions and the vanadium ions. The strontium haven't been included. And now we're going to cool down the sample to below the nail temperature. And so this is what the diffraction pattern looks like now. We have extra peaks. So these extra peaks are the magnetic Bragg peaks. We can take the difference between this temperature and this temperature to get the pure magnetic diffraction pattern. Now, if you do the calculation and the fitting, you find that the cobalt ions have this type up-down type order along these chains. We have antiferromagnetic order along C, and we have antiferromagnetic order along B between the chains, and ferromagnetic along A between the chains. Spins point along C. So now I'm going to talk, that was neutron diffraction. Neutron diffraction is used for investigating magnetic structures and crystal structures. So now I'm going to talk about inelastic neutron scattering. And inelastic neutron scattering is where we investigate excitations. So one instrument that's used for inelastic neutron scattering is the triple axis spectrometer. So here's a diagram of it. Now, let's think about it. So when you're doing neutron diffraction, you make an assumption that the initial and final wave vector of your neutrons is the same, of the same magnitude. But now we're interested in the difference. When we do inelastic neutron scattering, we're interested in any energy that the neutrons given to the sample. Because energy is related to wave vector, we're interested in the difference in length of the wave vector of the neutrons before and after the scattering. And actually, we need to measure this. This means that as well as having a monochromator, so if the neutrons come from the reactor and they arrive at the monochromator, and the monochromator chooses a particular wavelength from the white beam of neutrons. But what's important not only to measure or choose your initial wavelength, wave vector, or energy of neutrons, but also to measure your the final energy or wavelength or wave vector of the neutrons. So here we have the monochromator, and after that we have our chosen wavelength of neutrons, which of course means we've got a chosen kinetic energy of neutrons. Okay, they arrive at the sample scatters the neutrons. We choose to measure the neutrons that are going off in this direction. So here I got my scattering triangle. We choose to measure the neutrons going off in this direction at the angle 2 theta. That's why we've placed this here. Now this is an analyzer. And the analyzer is also a very well-known crystal where you use Bragg's law to measure. This time we're measuring the energy, we're measuring the wavelength of the scattered neutrons after the scattering event. So that's what happens inside the analyzer. Of course, if we know the wavelength, we know the energy. And then after the analyzer, we measure the number of neutrons. So we measure the number of neutrons scattered at the angle 2 theta that have an energy that we've selected using this analyzer. Here's the scattering triangle. So they're measured, and if we create an excitation, we're creating it at this wave vector Q. So here's a picture of an actual instrument. And of course, you can't see so much because everything is shielded. Anyway, the monochromator would be inside here and the neutrons would come along in this direction. Then there would be the monochromator inside the shielding block. Then the neutrons come out and this is where you put your sample. Then the sample scatters the neutrons and you choose to measure the neutrons that go off in this direction towards the analyzer. You can just see the bottom of it there, since the shielding's been lifted up. So the analyzer measures the neutrons that have a specific chosen energy, and then the detector measures the number of neutrons that have that specific chosen energy. Here's the scattering triangle. So actually doing a measurement, so when you do a measurement, when you do a measurement and you want to measure excitations, you can imagine doing different things. So one thing you might do is you might say, I know I've got an excitation at a particular wave vector, or I suspect I have an excitation at a particular wave vector. Therefore, I want to go to that wave vector in the sample, and I want to scan the energy transfer, the energy that I give to the sample. So here we say, okay, I'm interested, this is the reciprocal lattice of the sample, this grid. And I'm interested in this position, this reciprocal lattice vector Q. I think there's an excitation there. So I want to go there. That means I arrange my scattering triangle like this. And I want to change the energy. So at the moment, you could see that these two arrows are approximately equal. So probably I'm doing elastic scattering. I can then change the difference. So for example, I could keep Ki, Kf the same and change Ki, the length of Ki. Now I'm doing the same measurement, but at where I'm giving more energy to the sample. So I'm doing now an inelastic measurement, and I can keep changing the rate or the difference between Ki and Kf, changing the energy difference between the initial final neutrons that I wish to measure to scan energy. And it might look like this. So here we have wave vector. So let's look at this wave vector here. Here we have energy. And this is a scan. As you see these little dots, these were the points that were scanned, going up in energy. And then we can look more specifically there. We have count, number of neutrons, as a function of energy at this wave vector, and we see two peaks, which are these yellow streaks. Now, another way you can scan, of course, is that you can keep the energy constant. So the energy you give the sample can be kept constant, and then you can vary the wave vector. So keep energy transfer constant. That means keep the difference in length of Ki and Kf constant, but scan wave vector. So I want to scan through an excitation. So here, Ki and Kf has a particular ratio. Look at this point here, and then I change some of the angles on the instrument, and I can look at this point, but at the same value, but with the same values of Ki and Kf, or same lengths of Ki and Kf. So here we have some excitation. And this is wave vector, and this is energy, and now we're scanning in this direction. And we see, so if we take this plot, we see count versus wave vector, we're going to see these two peaks. Okay, so now there's another way in which you can choose your neutron energy or wavelength. So far, I just talked about using a monochromator crystal and an analyzer crystal, but you can also use distances and time. So of course, the energy of the neutron is its kinetic energy. So if we know its velocity, then we know its kinetic energy. So if we have a continuous beam of, this is a typical instrument, we have a continuous beam of neutrons, what we can do is use choppers to cut the beam into pulses. And we know when each pulse is created, so we have a time 0 for each pulse. And then we can measure how long it takes for the neutrons to pass through the instrument. And this gives us the velocity. So we'd have the neutrons coming in, there'd be a series of choppers, they would arrive at the sample would scatter the neutrons, these represented by these red arrows, into this detector bank. Now we've got a large detector bank. And these detectors would measure the number of neutrons, but also the time at which they arrived. If you know the time and you can measure all your distances, then you know the velocity. So now a bit more detail about these choppers. So the neutron is cut into pulses by choppers. This is what a chopper might look like. It's a disk which rotates, rotating disk, and the disk has a hole in the side. And so it can let through the neutrons once per rotation. So we have a first set of choppers, and they let through the neutrons. They cut the beam into pulses at known times t0. And then we have a second set of choppers, and these open at a time t1 later than t0. Now these choppers are placed at a distance, known distance L1 from the first set of choppers. They open at a time t1 chosen by us. So we know the distance, we know the time, so we know the velocity. Okay, then those neutrons arrive at the sample with their known velocity and therefore their known energy. So we got and known wavelength. So we know the energy of the neutrons that arrive at the sample. Then the sample scatters the neutrons. Then the sample scatters the neutrons and we measure the time of arrival in the detector. So here again, we have our first chopper. It chops the beam into pulses, giving a time t0. The second chopper opens at a time t1 after the first chopper. It's placed at a distance L1, so we know our velocity and our energy of neutrons, the initial neutrons. Then the neutrons arrive at the sample. The sample scatters the neutrons into a detector. All the distances are known. The detectors measure the time of arrival of the neutrons. Also, they measures their 2 theta angle and the number of neutrons. But from the time of flight, the time of arrival of the neutrons, we know the velocity of the neutrons after scattering, so we know our final energy. And so we know our initial neutron energy, our final neutron energy, and therefore we know how much energy we gave to the sample. The first chopper sets the initial time, the second chopper, and therefore sets the initial energy, and the detectors measure the final energy. Okay, so now I'm going to give an example of measuring spin waves, excitations, and measuring them. Well, maybe I shouldn't have said that. What I mean is, initially, I want to show you this graph. So this graph plot shows you the type of excitations that you can measure with neutrons, or it takes the type of excitations you get in condensed matter, from quasi-elastic scattering to rotational modes in molecules to phonons, acoustic, vibrational, optic phonons, spin waves, crystal field excitations. Now, neutron scattering allows you to measure these type of excitations. Actually, you can go further. You can even go, you can go to 1000 MeV. Okay, so now I'm going to focus on spin waves as a type of excitation. So when the magnetic ions inside a material interact with each other, we can write the Hamiltonian like this. Well, this is a simple Hamiltonian, but it often does take this form. So a Hamiltonian is a two-spin interaction between spin at position L and L dash, and the size of the interaction depends on the separation of these two spins. So we can talk about, now in my magnetic material, we can talk about a first neighbor interaction along the A axis, and the first neighbor interaction along the B axis, JB. Maybe we have a second neighbor interaction along the A axis. Probably further neighbor interactions are going to be 0. Okay, so this would be our Hamiltonian. Now in spin wave theory, we're going to assume we have a fully ordered ground state. So the ground state is ordered. We've got long-range magnetic order. All the spins are pointing, let's say in this example, they're all pointing the same way. We have a ferromagnet. Then the excitations are going to be small fluctuations about this ordering direction. And they can be calculated by diagonalizing this Hamiltonian to find the eigenstates and the eigenvalues. And when you do that, if your Hamiltonian is like this, you should get spin wave excitations. And here are plotted the spin wave excitations. Well, here we have a triangular lattice. It has 120-degree type order. And it has some anisotropy, which means that the spins lie in the triangular plane. And here we have a spin wave calculation for this triangular lattice, what we might expect to see in a neutron scattering experiment. So some more facts about spin waves. Spin waves have a quantum number of spin 1. And what you see here is typical in that the spin waves have a well-defined energy as a function of wave vector. And typically they have a sinusoidal type dispersion. And you can calculate spin waves. You can also use programs to calculate spin waves. For example, this spin W program written by my student Shandor Todd. So now to an example, this would be barium nickel vanadate. So in this material, it's the nickel that is magnetic. The nickel ions form a honeycomb lattice in the AB plane. So this is the honeycomb lattice. And these honeycomb layers are well separated from each other and they're stacked along the C axis. So we have 3 shown here. Now we can look at just one of these honeycomb layers. It looks like this. So here's the nickel ions. And then we have first neighbor interactions between the nickel ions, second neighbor, third neighbor. We also have interactions between the layers of the nickel ions, and we can have some anisotropies. So here in this Hamiltonian, we have first neighbor interactions, second neighbor interactions, third neighbor interactions, interactions between the layers, anisotropies that mean that the spins prefer to point in the plane, in this AB plane. And here's a powder measurement. So it's an inelastic powder measurement from a powder sample. This is functional wave vector and energy. Right, and now we also have single crystals. So this is a single crystal sample. It's about 1.5 centimeters long, 0.5 centimeter wide. So we can also measure the single crystal sample. So first we can measure, for example, at low energies, just go up to 12 MeV. And we see this type of sinusoidal dispersion, but we just see the bottom part of it. Interestingly, there are 2 dispersions. So we have 2 gapped dispersions if you take the cut here. Here's some more measurements, now going up to 30 millielectron volts. So here we see the full dispersion. This is along this reciprocal space direction. This is another direction. Here we have a direction which shows this slight minimum. And this is a obscure direction along a direction that doesn't have high symmetry, and we see this oscillation. Okay, so that's the measurement. So now we can take this Hamiltonian, do a spin wave calculation. We have to guess the values of the J's. We don't know them, but we can fit them, and then we can iterate and come up with the values. So then finally, here is the result. You can measure the spin waves. You can do the calculation and compare to the data. And the result you get from that is the values of the interactions. Jn is 11 MeV. That's the first neighbor. The second neighbor is 1 MeV. The third neighbor is approximately 0. We have some anisotropies too. Okay, I think I have 5 minutes left. Is this correct?
That's right. That's right.
So should I go to questions now? Probably. There are some.
If you would like, you could take 10 minutes also. It's okay.
Oh, this is dangerous. But I could talk a bit about quantum magnetism. But
that'll be nice.
Sorry?
That'll be nice.
Okay. Okay. I try keep it to 10 minutes. Quantum magnets. So far I talked about conventional magnets. Conventional magnets have long-range magnetic order in their ground state, and then they have spin wave excitations, and you can use neutron scattering to understand their magnetic order and to measure their excitations and to extract values of their exchange constant. But some magnets are not so simple. Sometimes you don't get long-range magnetic order, or at least it is suppressed to a temperature much lower than you might expect. And sometimes you don't have spin wave excitations. So these are quantum magnets. So there are cases where the system has strong quantum fluctuations that disrupt the magnetic order. So quantum magnetism, the ingredients for quantum magnetism are to have a low spin value, so spin half, not spin 5 halves, to have antiferromagnetic exchange interactions in general, or at least some, to have low dimensional interactions. And if we take the Hamiltonian, which is the sum of 2 spin Hamiltonians, H and M, like this, which is simple Hamiltonian, so it's a dot product, which can be written out in terms of its coordinates, which can be written in terms of its ladder operators. Then when this term dominates, we get long-range magnetic order, but anything that enhances this part, which creates fluctuations, can disrupt long-range magnetic order, in which case we expect that magnetic order is suppressed, at least to temperatures much lower than you might expect, given the sizes of the interactions. And when it does order, the size of the order is reduced compared to the size of the spin moment that is available. Typically, the excitations are broadened and renormalized. That means they have a different energy scale to that you might expect. And you can get unusual quantum numbers, like fractional quantum numbers. So I go through these ingredients. First, to have a low spin value. So if you have a high spin value, like spin 5 halves, then there are 6 different orientations that the spin can have with respect to a given axis. So now if you change the unit of spin by 1, for example, you go from 5 halves to 3 halves, which is not a big difference. But in the case of spin half, if you change the unit by 1, for example, using this part of the Hamiltonian, then you reverse the spin direction. The second ingredient was to have antiferromagnetic interactions. So let's say we have ferromagnetic interactions, all the spins point in the same direction. Now this ground state that is actually an eigenstate of the Hamiltonian. But if I were to draw the nail state where the spins point up and down, this state is actually not an eigenstate of the Hamiltonian. So let's just take two spins, these two spins coupled by a ferromagnetic interaction, and so this has a wave function, spin 1 up, spin 2 up. Now we act with a Hamiltonian upon it, and we get the same state. So this is an eigenstate of the Hamiltonian. But if you've got two spins, we've got an antiferromagnetic interaction between them. First spin is up, second spin is down. So we put up, down as our wave function, and then we act with the Hamiltonian on it. We get mixed in the state down, up. So the nail state is not an eigenstate of the Hamiltonian. So a long-range ordered state like this is not entirely true, or at least not with fully ordered moments. Now, the third ingredient is to have low-dimensional interactions. So if you take a three-dimensional material, and now we have a magnetic ion in the center, it's got 6 neighbors to the top, bottom, right, left, and front and back. And this is enough to stabilize long-range magnetic order. But in the case of 1D, so now that our magnetic ion only interacts to the left and right, then it doesn't have enough neighbors to stabilize long-range magnetic order. And a truly one-dimensional material does not have long-range magnetic order. It does not have Bragg peaks. So now I go on a bit. An example. So we take now all that ingredients. We have a one-dimensional chain. The magnetic ions interact in one dimension only by antiferromagnetic ions, and they have spin half. This was tackled by Hans Bethe. And he realized the ground state has no long-range order. 50% of the spins, I draw this, but this is only true over a short distance. This only has short-range order. Over a longer distance, some of these spins will end up being flipped. Okay, so Hans Bethe wrote the Bethe Ansatz, which was then a long-standing problem in condensed matter. Now, the excitations, it took another 50 years before people were able to understand the excitations of this system, which are spin-on excitations. So if you take the chain like this and you flip a spin from down to up, you create an excitation because you're costing energy because you've got antiferromagnetic interactions and ferromagnetic spin alignment. So this will cost this bond and this bond. But if you flip over more spins, then like 3, you still cost the same amount of energy. It's the ferromagnetic aligned spins that cost the energy. Similarly with 5. So unlike in the case of spin waves, where you think about single spin flip excitations, here all these excitations, which have different numbers of flip spins, actually have the same energy. And instead of thinking about flipping spins, it's better to think about these endpoints of the flipped region, the endpoints of the region of flipped spins. And these are known as spin-ons. Now, we had a spin half pointing down, which went to spin half pointing up. So total spin was 1. Total spin was 1 also here and also here. And that total spin 1 in the scattering event disintegrates into these two is shared between these two spin half spin-ons at the end of this flipped over region. So now we have spin half excitations. And there's a problem because when you do neutron scattering, your neutron scattering rule is that the change in spin must be 1, which means you can't actually see them. You can't create a single spin. So you have to create several at once. You have to create them in pairs. So while this might be the dispersion of a single spinon, we can't actually ever measure that. What we measure are pairs of spinons, like these two circles, these two ones here by the circles, or these two squares. And the act of measuring 2 at once means that we don't see a nice sharp dispersion like this, but we see a continuum of excitations. So seeing a continuum of excitations can be a signal that you have these fractional excitations. So now we go to 2006. Jean-Sébastien Coe solves the Bethe Ansatz. He predicts that we should see this scattering pattern as a function of wave vector and energy. And this is the 2 spinon continuum between this upper boundary and this lower boundary, or it's just multi-spinon continuum. So here is a material where we can now do a comparison, potassium copper fluoride. We measure it on a MAPS time of flight spectrometer, and we see this. This is raw data as a function of wave vector and energy, and we see the excitations coming up here, and they extend up in energy. And if you do the background subtraction, then this is what the data looks like, which can be compared to the calculation by Jean-Sébastien Coe. And you can do more quantitative comparison by taking constant wave vector cuts through the data. That's these red points. And constant energy cuts through the data, again, these red points. So, for example, this is a constant energy cut at this low energy. This is one at the high energy. And then it's compared to various theories. The all spin-on is the one from the latest theory. It's the solid blue, and it passes through the data and is a better agreement than the others. So this is to illustrate that the quantitative nature of neutron scattering allows you to quantitatively distinguish between different theories to find which one gives best agreement. Right, I need to stop. I go to the end. Yes. Yeah, just the summary. Thank you very much.
Yeah, thanks a lot, Bella, for the very nice talk. So are there any questions or comments from the audience here in the auditorium?
So maybe a bit of a naive question, but people always distinguish elastic and inelastic neutron scattering, but to me it always seems a bit strange, because if you have neutrons, how can you control whether they scatter elastically or inelastically? Do you know what I mean?
Yes, I know what you mean. Now, if you use a monochromator crystal and an analyzer crystal, like in the triple axis spectrometer, then you really do know, because you measured the energies of the neutrons, you really do know if the scattering is elastic or inelastic. Right? If you don't use an analyzer crystal, then you don't know, and you tend to assume, because the elastic scattering is stronger, that the scattering is elastic, or that's diffraction.
Okay, so essentially you do the same experiment, but you just filter the data that you get in the end.
Yes,
okay,
using an analyzer, yes.
Mm-hmm.
Or time of flight can also do this.
Okay, yeah, that makes sense. Thank you.
have one question.
Yes.
So in the inelastic scattering, you mentioned the neutron can create some excitation in the sample. Can
Yes.
it be the other way around? Like, can it carry some energy?
It can
Is
take
it?
away the energy from the sample also. Yes, you're right. Yes. Is that the question?
Yes. Yes.
Yeah. So for example, if you've got your sample, let's say it's at a finite temperature, so there's a thermally excited phonon, and the neutron can destroy it, take away its energy, and the neutron gains energy.
Okay. Yeah, I have one more question. Like in the one-dimensional cases, you mentioned it as quantum magnets, but in the later slides, the two-dimensional, and you call it frustrated magnets. Like, I'm wondering why such different names. Like you define quantum magnets as which doesn't have long-range order, right? If I remember.
Well, I only mean quantum magnets have strong quantum fluctuations, which can disrupt long-range order. Yes, not always though. In reality, they nearly always have long-range order in a real experiment, but it's suppressed to some low energies, so low temperatures. Sorry, was this the question? I don't know.
Yeah, but in frustrated magnets also we do have fluctuations, quantum fluctuations, right?
Yes.
So
also,
why different names? Like
oh well, I could have included frustration as a source of, as another thing that disrupts the order and leads to quantum magnetism. But I do want to mention that you can have classical frustrated magnets such as spin ice. So being frustrated doesn't have to be quantum.
Yeah. Thank you.
So you can have classical spin ice and quantum spin ice. Yeah.
In spin liquid, this dispersion relation is very clear, right? Whether it is magnon or spinon excitation. But if we consider disorder-driven spin liquid, then will it be the same magnon dispersion or spinon dispersion will get?
So disorder tends to broaden spin waves. Let's say you've got a disordered conventional magnet, then your spin wave excitations will be broadened. So it's not always clear. If you just see some broad excitations, it's not always clear that it's due to being frustrated or due to quantum effects. You have to use other information if you want to be sure.
Okay, thanks.
I have a question.
Yes.
Spin by itself is a quantum property. So why do we call like one as quantum and another as classical?
Yes, you're right. Well, if you got a sort of I mean, spin wave theory is a semi-classical theory, or you can do spin wave theory semi-classically, and it works just fine. So we say, well, spin waves basically. It's a good point, yeah. How to make the definition. Basically, you say, well, conventional magnets can be treated classically because the quantum fluctuations aren't important. But a true definition is I guess I can't give it to you. Or even maybe it doesn't exist. Or maybe someone else in the audience knows.
Yeah, thank you.
Hello. I have about 3 questions. First one is, you said about 2 processes. First one, when the neutron enters the sample, it interacts with the unpaired electron. And the other one, it interacts with the nuclei.
Yeah.
how do you distinguish which one happened, as in
Yeah.
elastic version?
Yes, so let's say you see a Bragg peak. So how do you know it's a nuclear Bragg peak due to the nuclear scattering or a magnetic Bragg peak? Yes, this is. Well, a Bragg peak is just a Bragg peak, and it's just a peak in the count in your detector. So you don't know straight away. So you have to use other information. So let's say you know that the material went through a magnetic phase transition because you measured the susceptibility. And you saw there's a magnetic phase transition. So you can be pretty certain then that the peaks that appear just below this at the temperature just below this magnetic phase transition are going to be the magnetic Bragg peaks. Yeah, you have to use additional. Okay, there's some other things like the intensities of the magnetic Bragg peak. There's a rule in neutron scattering that for magnetic Bragg peaks, you only see them when their wave vector transfer is perpendicular, or you only see them when the wave vector transfer is perpendicular to the direction of the spins. So when Q is perpendicular to spin direction, or you only see the component. So there's a directional dependence of the intensity of the peaks. And so you can, you don't get this with the nuclear scattering. So you can also check several Bragg peaks, similar ones, equivalent ones like 200 and 020, and you can use that.
One more, in the expression for the scattering expression.
Yes.
There was matrix elements of.
Yes, I'm finding it. Yeah.
This element has only the electron.
I can't hear you. Sorry. Are you saying here we have the states of the...
Why is the V nuclear not included in this?
Oh, well, it's V, and V can be nuclear or magnetic.
Okay.
Yeah. Well, it's really V nuclear plus V magnetic.
Okay, the last one. You had shown us two plots with constant Q and constant energy, and in both the plots we saw two peaks.
Yes.
The significance of two peaks, like why are we seeing two?
Oh, is it this slide?
Yes.
Okay, so we see, okay, so, well, it's a feature of the material, but if you have spin waves, so here we have spin waves, they tend to be symmetric about the Bragg peak. So you have a magnetic Bragg peak somewhere here. And then you have the spin waves coming out of the magnetic Bragg peak. And they tend to be symmetric about the magnetic Bragg peak. So if you scan, you're going to pass through both branches of the spin waves. But it's a feature of the material. So here we see two peaks, but it's for a different reason. We're actually scanning through that and that when we scan up. It's because the branches are split by anisotropy.
Thank you.
But what the peaks you see are just a feature of the material. They tell you about the material.
Any further questions? Any questions from the online participants? You can unmute yourself and ask.
was just wondering, how do you know what is a good wavelength of neutrons for a diffraction experiment? If you want to probe the structure of a magnetic order
Yeah.
or crystal structure. Yeah.
So if you have Bragg's law, then if you've got a large, they say 2d sine theta equals lambda. So let's say your d, which is your d spacing in your material, is very large, unusually large, then you might want to choose a large wavelength to match it so that you can measure it accurately. Or so it's based on the material, or if your d spacing is small, you might choose a smaller wavelength. Or if you're looking at magnetic scattering tends to only appear at low wave vectors. So then you tend to focus more on that with a large wavelength, whereas nuclear scattering appears at high wave vectors and low wave vectors, and therefore you might choose a smaller wavelength that covers a bigger wave vector range. So basically you need to match Bragg's law to your material.
I see, thank you. So do you also need to scan through different energies to get the best data, like you do an inelastic scattering?
So you're talking about diffraction?
Yes, yes, yes.
You choose a wavelength, and what you normally scan are 2 theta angle.
Okay.
You don't normally scan wavelength.
Okay.
If you're interested, but it can be advantageous to repeat the measurement with several different wavelengths.
Right.
To cover different ranges with different accuracies.
Mm-hmm. Thank you.
Yep.
Okay, then if there are no further questions, then let's thank Bella again for a wonderful talk. Thank you, Bella.
Yep.